All right, let's just dive right in, shall we? Welcome to our Grade 8 Physical Science Explainer, Light Reflection, Refraction, and Materials. Today, we're going to uncover the fascinating rules governing exactly how light travels and, well, interacts with the world around us. We're looking closely at some of those everyday visual phenomena you've definitely seen, and we're going to decode the actual science of how they work. So think about a time you dropped a pencil into a clear glass of water. If you look at it from the side, that pencil appears totally snapped in two, right? Or hey, maybe you've looked into a fish tank and noticed a single fish magically appearing in two completely different spots at once. No, these aren't glitches in the matrix. They're actual real-world phenomena rooted deeply in geometric optics. In this explainer, we're going to ground these optical illusions in everyday reality and figure out exactly why our eyes perceive these wild distortions.
Here's our roadmap for solving the mystery behind these illusions. First up, light rays and boundaries. Second, bouncing back, reflection. Third, bending light, refraction. Fourth, how materials affect light. And finally, a recap and transfer. Let's get to it.
Section 1. Light rays and boundaries. Okay, because light moves in straight lines, we can actually use simple geometry to describe its behavior. We model light using what's called a ray. That's literally just a straight line originating from a single point to show the path the light is traveling. Simple enough, right? But light doesn't just travel through empty space forever. It constantly bumps into matter, like a mirror or a window or a body of water. To figure out what happens when a light ray hits the surface of a new material, we use a super helpful tool called the normal line. Now keep in mind, this isn't a physical line you can see. It's a conceptual vertical line drawn exactly perpendicular, so 90 degrees to that boundary surface. Oh, and a quick heads up, while these visual models totally help us understand these interactions, the diagrams aren't always drawn perfectly to scale.
Moving right along to Section 2, bouncing back, or reflection.
Now, whenever you look into a mirror, you're obviously seeing a reflection. But how does that work geometrically? Well, it's governed by a very strict fundamental rule known as the law of reflection. When our light ray approaches a boundary, the angle it comes in at is called the angle of incidence. And when it bounces off, you guessed it, that's the angle of reflection. Here's the golden rule, the one you absolutely need to remember. We always measure these angles relative to that conceptual perpendicular line we just talked about, the normal line. And according to the law of reflection, the angle of incidence exactly equals the angle of reflection. Whatever angle the light comes in at, it literally has to bounce off at that exact same angle. All right, let's do a quick pause check to test our understanding of how this bouncing works. Here's your question. If a ray of light hits a smooth mirror at exactly a 45-degree angle relative to the normal line, where does it go? Take a second and think about that rule we just established. Okay, here's the immediate reasoning. The light reflects at exactly a 45-degree angle away from the normal on the opposite side. Because of the law of reflection, the angle going in absolutely must perfectly mirror the angle bouncing out. So if the incidence is 45 degrees, the reflection is 45 degrees. It really is that precise.
Which brings us to Section 3, bending light, also known as refraction.
So what happens when light actually passes from one medium, like air, into another, like water? It changes direction. It bends. But why? Well, there's this absolutely brilliant analogy of pushing a lawnmower that explains this perfectly. Just imagine you're pushing a lawnmower from a smooth, fast, paved footpath, and you're pushing it diagonally onto some slow, thick grass. Because you're hitting the grass at an angle, one of the front wheels is going to hit the thick grass before the other one does, right? That wheel hits the grass and slows down, but the wheel that's still on the smooth pavement, it keeps moving quickly. So what happens? The whole lawnmower gets violently pulled to the side, changing its overall direction of travel. You know, light behaves exactly the same way as a wave. When one side of a light wave hits a slower medium before the other side, the light slows down asymmetrically. This bends the path of the light ray closer to our perpendicular, normal line. And that phenomenon right there? That's called refraction.
Section 4, how materials affect light.
Now, different transparent materials have entirely different properties. We measure this using a value called the index of refraction. Basically, the higher the number for the index of refraction, the slower light travels in that specific material. For instance, air has an index very, very close to 1, meaning light travels almost at its maximum speed. But consider a diamond. Its index is a whopping 2.419. That means light slows down significantly when it enters a diamond. And because the change in speed from air to diamond is so massive, a ray of light is going to bend drastically when making that transition. The specific properties of the material directly dictate the speed and therefore the amount of bending.
Time for our second pause check. Let's apply our lawnmower analogy to these material properties.
Based on the data we just looked at, will a light ray bend towards the normal line or away from the normal line when moving from water out into the air?
Let's break down the immediate reasoning here. Water has an index of 1.333 and air is about 1. So light is moving from a slow medium into a fast medium. Imagine our lawnmower exiting the thick grass diagonally back onto the fast pavement. One wheel hits the smooth pavement first and suddenly speeds up, while the other is still stuck in the grass. This sudden speeding up of one side pulls the lawnmower, or in our case the light ray, away from the normal line. And honestly, this brilliantly illustrates exactly what's happening with our broken pencil illusion from the very beginning of the explainer. When the light rays traveling from the underwater portion of the pencil exit the water and enter the air, they speed up. They bend away from the normal line before reaching your eye. But your brain assumes light always travels in a perfectly straight line, so it projects that bent ray straight backward, which makes the pencil look completely snapped.
Finally, Section 5, Recap and Transfer. Let's bring this all together.
So the absolutely crucial point to take away from this explainer is that light travels in straight lines until it hits a boundary. When it reaches that boundary, which remember we model conceptually using a normal line, two main things can happen. It can bounce off, that's reflection, where the angle of incidence exactly equals the angle of reflection, or it can pass through and bend, which is refraction. This bending is entirely driven by the fact that light changes speed depending on the material it's traveling through. And as we just saw, materials with a higher index of refraction slow the light down a lot more.
Now, I want to leave you with one final kind of provocative transfer question to challenge everything you've just learned. We know that when light moves from a slow medium, like water, into a fast medium, like air, it bends away from the normal. Well, imagine you just keep increasing the angle at which you shine that light from underwater. Eventually, the refracted ray is going to bend so far away from the normal that it hits a flat 90 degrees, literally skimming the surface of the water. So if you angle it just a tiny bit more, what happens? Could the light be blocked from exiting entirely? Could it undergo what physicists call total internal reflection and simply act like a mirror, bouncing entirely back inside the water? Think about how this exact principle of trapping light inside a material might just be the key to the optical fiber cables that literally power the internet you're using right now. It is a really fascinating concept to ponder. Keep questioning, keep observing, and thanks so much for joining me on this explainer.